So hey guys, in this video I'll be demonstrating how we can go from VDO.Ninja into OpenCV or similar applications. So if you want to stream WebRTC video from the web into your computer vision framework or your machine learning framework like Tensorflow, Keras, whatever, this video is for you. I get asked quite a bit on how to do this. I've long provided code called Raspberry Ninja that lets you go from VDO.Ninja into Python, but I never really walked through the details of how to go from that incoming video, decoding it into individual frames, and then making those frames available to Numpy or whatever framework that uses it. So I'll be covering that in this video. To demonstrate what I'm talking about though, here we have VDO.Ninja, and here is a motion JPEG output of that video. So I can open it up and we see that this is an image that's animated. I can have multiple viewers. It's hosted locally on a local small embedded computer. Yeah, the latency here is 1, 2, 3, 4, 5, So the latency here is very, very low, under a second. And we are going from WebRTC on this computer to another computer, and then into a Python script that's taking these raw frames given to it by Raspberry Ninja, and then hosting those raw frames as a series of motion JPEG images, and it's self-hosting it on a server. Now this is an example of how you could pull these raw frames into your OpenCV. I'll walk through by the end of this video how to do all this, and I'll be explaining the code, what each step does and why. There'll be chapters in the video description if you want to jump ahead to certain parts, because this will probably be a longer video that will be probably dry at certain spots. Now, if you don't know what the Raspberry Ninja project is, you can go to Raspberry Ninja. You learn about it here, and you can jump to the GitHub page. This is an open source project, so you can download the code, run this on a Linux computer, Raspberry Pi, Orange Pi, Jetson. It even runs on Windows. And the primary purpose of the Raspberry Ninja project was to let you publish video from a Raspberry Pi or some other system into VDO.Ninja, but it also can pull video from VDO.Ninja into itself. It can record video to local disk, but in this example, I'll be demonstrating how you can decode the video into raw frames to make use for things like OpenCV. And those examples will be stored in this folder. The folders and the details of this project will change over time, so take everything you see with a little bit of grain of salt. This convert to NumPy example folder will probably change over time. In it, currently there's an advanced example, which is what you see here, this notion of hosting JPEG images. But there's also a more basic example. So kind of like the bare minimum code that you need to add to your project to access the raw frames. You don't need to incorporate Raspberry Ninja into your machine learning project. You just need to include a little bit of code. And we'll cover this little bit of code, but this lets us access these raw frames easily, virtually in any Python system. All you need to do is have Raspberry Ninja running in a separate process. You don't need to modify it to make it work. Okay, so pretty straightforward. Let's get started, I guess. I'm going to cancel and clean up what's been currently running. So I had on the right here Raspberry Ninja running. On the left, I had the code that was converting frames into JPEG. So that was the advanced code example. Okay. If you don't have Raspberry Ninja installed, you can follow the install instructions. I won't cover it too much, but the basic idea is git clone, install the repo. You then go into the repo, and the main file that we want to deal with is called publish. It's in the folder publish.py, and we can run it by just typing run Python publish py. However, in this example, we're not looking to publish video. We want to view video and save it as a frame buffer. So we have a command called frame buffer. Okay, and this tells the system that we're going to be pulling video and we'll be using the frame buffer feature. It can't do at the moment more than one thing at a time. You need to run multiple processes if you want to do more than one thing at a time. So it will currently only work as converting video into a frame buffer, but this might change over time. We can give it a stream ID name. So Steve123. And that technically is sufficient, but just there's a few other commands I'll add on. I'll add H.264 and no audio. The reason I'm doing this is H.264 works a little more reliably. It can be hardware accelerated on the system I'm running with, so it's more performant. And I don't need audio. The frame buffer does not currently work with audio. It only works with video. So if we pull audio, we're just wasting bandwidth and resources because we're not going to be using that at all. Okay, and then we can hit run. Now, if you're familiar with Raspberry Ninja, the first part, you're probably familiar with ping pong, but these intermediary steps is specific to the frame buffer. It's showing you that these frames are being brought in and decoded, and it's just mentioning on screen a frame of this size has just been decoded and put into the frame buffer. Okay, I'm going to stop it and we'll dig into what's going on there a little bit. This system I'm running on is the Orange Pi 5 Plus, 16 gigabytes of RAM, 8-core ARM processor. It was about $190 Canadian. Great system. You might not achieve good results if you're using a Raspberry Pi, maybe with a Raspberry Pi 4 if you limit the resolution. But this decoding video, converting to JPEG, it does take some bandwidth. So if you have like a Raspberry Pi 2, this may not work. And you might need to fiddle with other aspects along the way. Okay, we're going to go in and look at the code. Okay, so I already have this marked here. When we activate the frame buffer command line parameter, it triggers this bit of code here. So it tells our GStreamer pipeline that what we're trying to do, in this case, we're actually going down here because we're dealing with H.264, so we're going to decode the H.264 video. In this case, we're using a software decoder. I'll open H.264. We're going to convert the raw frames into BGR format. BGR is what OpenCV uses. You can always change this to something else, but you could also change it on your end. So it's BGR, which means blue, green, red, the order of the pixels. And then we are putting these frames into a queue. Now this queue is currently being set to a size of 1. And I'm saying that this queue is leaky, meaning that if more than one item ends in queue, don't wait for the queue to dry up. Simply get rid of the old item in the queue. What this means is the video is being decoded and put into a spot, but it's only keeping the most recent last frame. The reason is if your system is slow or you're not pulling frames out of the queue fast enough, you'll start to have added latency. Over time, if you have a slow system that can't keep up, you might find the video is 30 seconds behind. So by adding a limit to the buffer size and telling it that we want to leak data, we can make sure that the buffer is always fresh. So anytime I pull from that buffer, the data will be the freshest, most recent decoded frame. Excuse me. Now I cannot add this leaky concept upstream before I decode video because compressed video needs to be intact. If I try to drop compressed video before decoding it, things would go bad. It's more important to tell the sender to lower the resolution or lower the frame rate than it is to try to drop it. You can't simply drop the video. Now, because of that, you might notice that I have Q equals 2 on the VDO.Ninja sender page. By pushing higher resolution video into the Orange Pi and decoding high resolution video at a higher frame rate, it puts more load on the Orange Pi here. So it starts to lag and fall behind, regardless of having that frame buffer of 1. By putting Q equals 2, I've set the capture resolution to 640 by 360. Okay. Now I can always lower the frame rate lower as well. Go here and I can always lower the frame rate to, let's say, 13 frames a second, 15 frames a second. Okay. So now it's publishing at a low resolution at a low frame rate. And if you have a slow Raspberry Pi, you can try setting the frame rate and the resolution to something low on the VDO.Ninja side so that instead of having to drop compressed video, you can just reduce how much compressed video is being received. That makes the rest of the process easier, okay? No point sending more video than what your buffer can keep up with. Okay, so jumping back in. So that's pretty much it. And then this last part here is called AppSync. You don't need to worry about that as much. This is an internal to the publishing script itself, but it lets me pull frames out of the buffer and make it available in a secondary buffer that can be accessed by another application. If you were to take the Raspberry Ninja code and add your own code to it within the same sort of process, you could read from this app sync directly and skip the next step. But the next step that I'll be demonstrating allows us to share this video data across multiple processes, multiple scripts of Python. So you don't have to build on top of Raspberry Ninja. You can have that be its own standalone process, which is, I think, preferred. So to see what we're doing on the AppSync side, we can jump to it. And what we see here is, my head's in the way. We are creating something called a shared memory. We're reserving a little bit of the RAM, and I'll be simply writing these frames to that shared memory buffer. I've given that shared memory buffer a name. Now this might change over time. I'll probably change it to something more dynamic. I just have a placeholder for stream ID, but in the future it would be your stream ID probably here instead, so it would be unique to each viewer. But yeah, so this shared memory is, you can dig through the code, is being accessed where? Here. So this little bit of code here is dealing with, is making the raw frame available to the shared buffer. I think I was being a little bit clever here. You don't have to write to a shared buffer. In another project called Oobleck, let me jump up here and show you this other project called Oobleck. I did this project years ago, but does the same thing. It takes WebRTC, brings it into OpenCV, TensorFlow, anything like that. I abandoned the project more or less several years ago and open sourced it. But in this project, the notion was the raw frames actually went to a Redis server, or maybe JPEG images or PNG images went to a Redis server. And those frames then were available to multiple viewers and multiple systems not connected to the same computer. So you can review what I did with Oobleck. I did this, ages ago, 7 years ago-ish. It's ready to go. Probably getting some dust on it though. But in this case, we're saving to a Redis cache, making these loosely compressed images, PNG images, for example, or JPEG images available to many people. And Redis is fast enough to handle this no problem. But jumping back to our example here, I'm writing to a local memory buffer. And it's a shared memory buffer, so it's kind of nice because other applications on the same computer don't have to download the image really. That buffer is available to them as well. So I'm not uploading an image to a server. The image is just being put into a buffer and it's being made available to any application that wants to read from that buffer. This saves on network overhead and complexity. So this is a very low-level way of sharing the frames cross-application. There are some limitations with this though. For example, VDO.Ninja, the frames, the resolution that we're publishing with changes in resolution at times depending on network performance and things like that. It's dynamic. So if I'm writing to a shared buffer that has a fixed size, the receiver doesn't know what size frame I'm putting in that buffer. It doesn't know the information about it. So I needed to put a little bit of a header on. So when I pull up here, I pull the frame from the GStreamer pipeline, right? I now get the width and height of that frame from GStreamer, and I have now this raw frame. It's now available in a Numpy format. Cool. And I print to screen that information. That's what you see gets updated on the screen. Now I have it set here that the frame buffer will be a max size that can fit 720p video. So at the moment, if you put 1080p video into this frame buffer, it would fail. It wouldn't be big enough. I'll probably adjust this in the future to be 1080p instead. But for this example, it's just 720p. However, we know that we're pulling in 360p video. So it wouldn't fill this frame. It's smaller than this frame buffer size. So what I do is I reserve the first 5 words, the first 10 bytes of the frame buffer for metadata. This might change over time as well. It's not set in stone or anything like that. But the first 4 bytes, the first 2 words, define the width, and then the second 4 bytes define the height. So 255 times 255, technically I could define up to 65,000 resolution. Anyways, and then the fifth double byte has a counter. It only goes to 255 and then resets. But this way you can tell if the series of images you're getting, whether you missed a frame. You can also tell if it's the same frame as last time. So when you read from the shared memory buffer, you can always tell if that if the current frame in the buffer you've already read from, or whether you haven't read from, or whether you skipped a message or skipped a frame. So we have an ID and we have a width and height. And we also know that we're writing to it in BGR format. So this string here flattens the image from a 2.5 dimensional image down to a 1-dimensional image. And we write the order as it is seen in memory. So when we destructure it, or sorry, when we reshape it, it should maintain the BGR blue, green, red ordering of the frame and rows and things like that, okay? Now, this next part here is optional. It's happening regardless, but you don't need to use it. You can just read from the shared buffer however often you want. But just in case you want a signal to be notified when the frame buffer gets updated, I send a little ping to a UDP socket port locally, 1, 2, 3, 4, 5, 6, just saying updated. I could include the metadata in this update. However, that's asynchronous to the actual shared buffer state. You might get this message, check the shared memory buffer, but it might have changed in that split second. And so the width and height might have changed, which is why I fix the frame buffer width and height metadata to the frame itself. And I only rely on triggering a notification, just saying it's ready rather than giving any metadata. You can ignore this on the viewer side, but it's there if you want it. Okay, so that's the end of the code that's added to the frame buffer. So we're decoding the video, we're grabbing the frames, and we're pushing them into a shared memory buffer. Now here, we're going to do look at a basic example. I'll just jump to the bottom where the main code is. You don't need to create a process, a multi-process, but I am. So essentially I'm spinning this up into its own little sort of thread, let's say. But you can just run this code outside of a thread as well. This is just helpful in case you don't know how to do multi-processing. This is just a simple example of that. But what we're doing is we open that shared memory. The shared memory name is here. You might need to specify your stream ID in the future so that it opens the correct shared memory. But this is being accessed in a read-only mode. If the shared memory does not exist, it will keep retrying until it does exist. Okay. I tell it how big the shared memory is, 720p plus 5, because the 5 is the header, and then 720p is the reserved space. The frame may not actually be that big, though. There's a nice little trick here. I linked to how I found the solution to this, but when Python closes, it automatically destroys the shared memory buffer, which is a problem if you're a viewer and you close it. It's going to clear the shared memory buffer, preventing other viewers from now viewing that shared memory buffer in the future. So to allow us to have multiple viewers and to be able to start and stop the script as we want, we deregister the shared memory buffer. So we make it so that Python no longer tries to clean up after it. This means we have to trust in the Raspberry Ninja code to clean up the shared memory buffer when it stops. And it should do that. If you don't, you get memory leak problems and lost children, I don't know what. The point is, this is not documented, but you need it if you want this application to work reliably more than just once. Other than that, there's not too much magic involved. We are copying the frame buffer locally. If we don't copy the frame buffer, and we work directly from the frame buffer, we can do that, but we don't know what other viewers modifying it. And we also don't know if it's going to be corrupted down the road when the publisher rewrites and updates that shared memory buffer down the road. So to make sure that we have a snapshot that's not mutating, we're going to copy it into this variable. And now we're good to go. We have our NumPy array essentially now available. Like this is a Python buffer, and now we convert it with NumPy into a NumPy array. We know that the first 5 words define the metadata, so we copy that into a separate value. I make sure that the frame, this is the frame ID, make sure that the frame ID I haven't already downloaded. I don't want to go through the hassle of processing it if I already processed it before. This shouldn't trigger necessarily always if we're using events, the emit update command. But since in this case we're just sleeping and we're just mass pulling the frame buffer, this is probably going to trigger a few times in between intervals. And this just means, oh, we pulled this new frame, but we already know what this frame is. Let's try again. So we're just brute forcing until we get a new frame. Once we get a new frame, we grab the width and the height from the metadata. Right, so this just pulls the width and height, does the math needed to give us the width and height. And then the final step is we crop the image. So we remove the header information from that NumPy array. Now that we know we removed the header, we can then reshape it to the width and height that we expect. If everything worked correctly, we should have the correct size array, 640 by 360 in this case. We should have no issues. Let's, I guess, try it. I haven't actually run this in a while. So what I'm going to do is I'm going to run the publish app. Wait for it to start going. You don't have to wait, but it's going. Let's check the file name. Let's run it. Python basic. And there we go. We see that the width and height is 640 by 360. Whatever. It's 360p. And yeah, it doesn't do anything more than that. This basic example just prints to screen the width and height. And it's virtually in sync exactly. You can start and stop it. Continues. Right? We can actually have multiple viewers accessing this locally as well. So that's the very basic example. So if you wanted to play with this, you can. I'll show you that if I put print dupe here and I rerun it, we'll see that it says dupe a lot, and every now and then there's a flash of an actual image. So we're checking the frame buffer far faster than we need to, because our frame rate's only 15, and we're checking at 60 frames a second here. So let's lower this interval down to something that's a little more in sync. Still, I know why. Let's move this here. There we go. And let's get rid of that altogether. There we go. So now we're a little more in sync, where we see it's a duplicate. We now wait a fraction of a second before retrying, but more in line with what we're expecting. So this is getting pretty efficient. Now this is just brute forcing. Let's take a look at the more advanced example. So in this more advanced example, I'm going to try to import OpenCV. If it can't find OpenCV, it's going to try to import Pillow. OpenCV is a little bit hard to build or compile on a lot of systems, while Pillow is pretty easy to install. And since all we need to do is convert from Numpy into JPEG, if you don't have OpenCV installed to run this demo, just make sure you have Pillow installed with pip install Pillow. Okay. Anyways, we go down here. We see that we are opening up a Scikit server on port 12345, and we are listening to it. Okay, so we bound to it, and now we're listening to it. Only one script can bind to the port at a time. So in this case, we can only have one viewer. We can't have multiple local viewers because the socket is already being used. But we also open up the shared memory buffer, just like what we did before. One of the key differences is instead of brute forcing and trying every fraction of a second to see if the shared memory buffer is available, what we're actually doing is we're waiting on the Scikit server that we just opened. We're waiting for something to poke it. And when something pokes it, we say, haha, something new is in the frame buffer. And then we start pulling from the frame buffer. If for some reason we don't get something, if we don't get a new frame and it persists, I'm going to assume the publisher actually stopped, and it's going to continually try to retry now to that frame buffer. We don't need to worry about this. Yeah, we continue down the script. We already talked about this. We get the width and height, and then we cut the header off, and we get just the frame shaped. So we're at the same point now as we were in the previous example. However, if we have OpenCV installed, we can now encode it to a JPEG image. And if we don't, well, it's going to fail. It's going to try using Pillow instead to convert the Numpy image into a JPEG image. This little bit of code here converts from BGR to RGB. So if you need a simple way to do that, you can refer to that. That's simply because Pillow takes RGB, not BGR. But we also get a JPEG image. We'll get to the next step, to this promise part in just a second. We now have this JPEG, and we want to host it on a web server. Now, this web server doesn't know when the frame buffer was processed and that frame is updated. It's running its own sort of thread. So as a user, whenever I load up this image, it sends a message to the server here saying I'm requesting, well, it's actually going down here and saying I'm requesting a website, and it returns the website with the JPEG image linked, and then that queries this. Anyways, I won't go too much into how Motion JPEG work, but essentially what we're doing is we're running a header saying that's going to be a multi-part response. So until I say it ends, it's not over. And each part is defined by a boundary, which I define here. And essentially, I'm just drawing new JPEG images into the stream. saying at each chunk, this is the next part, this is the next part, this is the next part. And the browser understands this as a series of JPEG images, and it just rewrites the old image with every new inbound image. So in this case, I'm just looping, getting the frame recreated, which is now JPEG, and drawing it into the buffer, into the stream for the viewer to actually see. Now, it's not efficient for me to just go through at 15 frames a second and send the same image if it hasn't updated. So I'll show you that there's this neat thing called an event in Python. You can use something called await and a future, but this web server doesn't support asynchronous operations. So I cannot use like a synchronous future operation as a promise. So I'm using something called an event. And essentially what I'm saying is wait until the event has been triggered. And if not, just keep waiting until it is. So it's kind of like an await future or promise, but without having to use asynchronous functions. Anyways, kind of cool. So I include the code here and it demonstrates it here. You might find this useful in your own application. If you're doing a multi-threaded application, you might want to wait until the image has been updated. So this clears it, so it becomes unset, and then we can just wait until it is set. And we'll just wait in the loop until it's available, and then it will draw it. It only gets stuck in that waiting state if it sees the last frame and the current frame are still matching. And it knows what the last frame is based on what's in the global buffer. I could just put this into a loop and say sleep 1 second, but that's 1 second of added latency. So with this, by using an event, I don't waste any time trying. So the event is set up here. It's a global. And essentially what I'm doing is every time a new image has been processed, I trigger the event saying, hey, it's now set. It's now ready. It's very similar in that same concept to what we're doing with the socket, where when it's ready, we poke the socket. In this case, we poke the event. You could write your code into this process, let's say. So every time a new frame comes in here, you could process directly here. The reason I have to use a set is the web server is in its own separate thread. So I need another mechanism to keep track of when it's ready and when it's not ready. Okay. So yeah, that's the code. To make this work again, we just run publish in frame buffer mode. It's going to start pulling our video frames and converting them to raw images. We can then start our advanced script. It says OpenCV wasn't found. We're switching to pillow mode. And then we can switch over to our web server. We type in the URL of the device. In this case, it's the Orange Pi at port 81, IP address 14, and we run it. And now it triggers the stream to start streaming in. And as long as it doesn't lose a network connection, it will update the frame here whenever it's processed and ready automatically. Because we use these asynchronous events, or these like promise events and UDP triggers and emits and things like that, what we are able to do is go from VDO.Ninja into here. And as we see, the latency is really, really low. On a faster computer that can process JPEG images faster, and that can decode video faster, etc., you can lower this latency down even more. Yeah, really kind of cool. Now, I'm going to switch over and I'm going to just show you that we can do more than just JPEG images as well. So let's do a little bit of computer vision. Oops. Let's open up the advanced code. I already had some code here pre-written for you guys here. So I'll just comment it out. I was trying to think what's some very simple computer vision I could do that doesn't require anything installed, just using Numpy. So I thought some sort of edge detection would work. So what I'm doing is I'm taking the last frame and the current frame, subtracting them to make a very basic sort of edge detection. And then I'm going to so we're doing that. Let's switch over to this. There we go. So let's open up the to show you the so it only shows the delta, the difference between the previous and last frames. Anything that's non-changing gets hidden. The Twitch logo gets removed, for example. The audio bar only shows the amount of change. So this is perhaps very low-level, easy code if you wanted to do like some sort of security camera. If you had a fixed camera outside pointing at your driveway, you could wait for something to change, some sort of large object to appear in a frame. You could then draw a bounding box around it, track it, record it. Rather than recording the entire frame, you can record just things that move, motion essentially. Or you can just use this as saying, if enough pixels have changed, start recording or stop recording, and now you have a motion sensor. Yeah. Very, very simple computer vision, right? And that's the end of that. So all the code is available in here. The very basic code you need without anything advanced is just listed here. It's up to you in this case to manage all the other stuff like events and whatever else. But this is the core code you need to pull a frame out of the shared memory buffer. I've done a lot of cool stuff in the past. This Oobleck project here did a deep fake. So the idea was it would take your face from a webcam feed, stream it to a server, apply a deep fake model to it, and then show your deep faked video back to you as a video stream. The concept of this project was for deep fake detection. So if you had an inbound live stream, you could apply deep fake detection to the inbound video stream. And so detect deep fakes within a sub-second from a remote server. You could do other things, you could, whatever else, but this is the application. Much more complicated than Raspberry Ninja. But you might find it still useful if you wanted some aspirations and ideas on what you can do, to further scale out your projects. Okay, thank you for watching, guys. I know that was quite a lot. Raspberry Ninja and all the code we talked about is continuing to evolve. Hopefully it helps you on your project, though. So if you are doing a WebRTC project, you're welcome to use VDO.Ninja. And Raspberry Ninja is there to support you. And if not, hopefully my code examples can get you unblocked and going. Because I gotta say, guys, GStreamer, Linux compiling video, WebRTC, all that, it's a lot of time. And as helpful as ChatGPT is, it does not know enough to do it for you yet. But maybe in the future it will. Probably not too that long, not far off from it being more helpful than I am. But yeah, anyways, thank you for watching. I'm on Discord at discord.video.ninja. Join the Raspberry Ninja channel if you want to talk about this project. Otherwise, check out the GitHub and have fun. Bye-bye.